Good morning, my name is Meng Lu. This video record is made for the EGU 2021. We are going to present our works on global high-resolution statistical modeling of nitrogen dioxide. Our goal is to map nitrogen dioxide at the global scale, but with high spatial temporal resolution. Nitrogen dioxide is a gaseous air pollutant which is commonly produced as the result of road traffic and can also come from fossil fuel combustion. So why do we want to do it globally? The primary reason is that in many countries there's a lack of ground stations. This figure shows the darker the color, the less ground air pollution stations there are, and therefore those countries are more dependent on the satellite imagery for an estimation of the air pollutants. But the satellite imagery, it has of course a very coarse resolution and doesn't provide details at the street level. But many of these countries are very, for example, African countries, the people there are very vulnerable to the air pollution, especially children. They are suffering a lot. And another reason is that a global model is contribute greatly to a consistent epidemiology studies to be carried out worldwide. And why do we want to do a spatial and temporal with a high spatial and temporal resolution? It is because the pollutant like nitrogen dioxide is highly dynamic in space and time. So this is here you can see a map that we made for Utrecht, and you can see that there's a strong spatial temporal dynamics over the city during the 24 hours of a day. And our method is based on statistical modeling, which is to find relationships between nitrogen dioxide and geospatial predictors, and also to model the spatial and temporal dependency. So one work we published in 2020 is provide us preliminary foundations. We carried a set of comparisons. The first is the comparison between machine learning and linear regression models, and then we compare global and national models, which has dense ground station networks. So we know that how different it is between the global and local models. And we also compare day and nighttime models, which is also important for the exposure assessment because people have very different activity patterns between day and night. And our study is also highly motivated by the Sentinel-5P satellite, which is the topomy instrument on board of it. Since 2019, the sensor is going to have a 5.5 kilometer resolution, which is much higher than any of the precedent sensors. And we found that with the air pollution, with the machine learning model, we generally got a higher prediction accuracy, and more importantly, the differences between the national models and the global models are smaller compared to a linear regression model such as Lasso. So that is a very promising sign showing that we could develop a global model with an accuracy that is close to a national model with dense ground station measurements with a more flexible model. And we also see that you can also see the prediction pattern from the machine learning models are more realistic. So you see this more gradual diminishing from the city centers, from the cities to the urban areas. But this pattern is less obvious from the Lasso model. But we also found that despite many machine learning models obtain very similar prediction accuracies, the prediction patterns are actually very different, and also between the national and global models. So this is very alarming. we carried out more validations. So we use mobile measurements and then to better compare our models. So our challenges in the statistical modeling is first of all, how can we better model the spatial temporal variabilities considering joint spatial and temporal correlation, and how do we model the spatially heterogeneous relationships between response and predictors. So for example, different countries has different regulations, different emission standards. How do we take them into account when we are building our model? And also, how can we integrate more spatial information instead of only based on point, on the point data, so the point-wise regression. In our current study, we collected most comprehensive set of ground station measurements hourly, and we updated the geospatial predictors, and our ongoing work to firstly produce a product which separates between weekdays and weekends, additional to the day and night, and using our XGB model, which we found to give the best prediction result. And we are also working on hourly spatial temporal models and hierarchical modeling. So we invest in mixed effect models and deep convolutional neural networks to extract information directly from images and to account for all the, so in this way we account for all the neighborhood effects. So this is a global map we made using the XGBoost, and this is for the daytime and weekdays. So you see that we actually already have quite good prediction patterns, quite reliable in space and time, and the local details also very well presented. So here we are showing the differences between day and night models and weekdays and weekends models. This is cropped in the city of Vienna. So you can already see there that there's a big difference between day and night. You see, and also weekdays and weekend. You see the highest concentration during weekdays and daytime along roads, and the pattern is more smoothed out during nighttime. So thank you very much for your attention, and please contact me if you had any comments.